Okay, good morning, everyone. Welcome back from our Thanksgiving break. Today, we're honored to have Professor Piotr Fryzlewicz from London School of Economics to speak for us. So, Dr. Fryzlewicz's research is about change point detection and inference recently. So, prior to working at London School of Economics, so Dr. Fryzlewicz obtained his PhD from the University of Bristol and studying the wavelets in statistics. And then he spent a brief period of time in the late 2000s working in the finance industry. And then he returned to academia to work on the change point detection inference and non-stationary time series. He was the former editor of the Journal of Royal Statistical Society's Series B, and he has been a keen statistical consultant. So the paper he's going to discuss today is kind of special. It's a milestone in his career because it's his 50th journal length paper. So let's welcome Dr. Fryzlewicz to talk about the narrow significance pursuit about inference on multiple change points in linear models.
Thank you very much, Jessica. It's a great honor to be here and to speak in your seminar series. I should start by saying that Jessica extremely kindly moderated my bio sketch because I only mentioned that this is based on my 50th piece of work because this realization made me feel rather old, which is what I said in my bio sketch, but she very kindly cut out that piece, that self-reference to my age. So I thought it was very, very polite of her. But this talk will be about making statistical significant statements in the problem of detecting change points, detecting change in general perhaps, and in particular detecting change points in data, in time-ordered data. Now, recently there has been a lot of work on a posteriori change point detection in data sequences in time series or perhaps in spaced index data. And I was trying to understand where this increased interest came from really. So I came up with those possible reasons. One is the emergence of computation efficient algorithms for segmenting sequences, for multiple change point detection in sequences. For example, there's this algorithm called PELT, which is a dynamic programming algorithm for fitting the best least squares piecewise constant function signals to data, which sped up things enormously. There's wild binary segmentation, which I authored a few years ago. There's the narrowest over threshold algorithm for both are sort of pseudo greedy algorithms for segmenting data sequences, for detecting changes in not only in the piecewise constant levels but also in piecewise linear trends. So there's a lot of recent computational advance, I would say. That's one pillar of, I think, of why there has been such renewed interest recently. Another reason is, of course, as we all know, the continuing emergence of modern complex data types. So we're talking about networks, high-dimensional panel data, etc., which from the perspective of the associated applied problems require sometimes change point detection approach. And there are ever more science problems requiring high precision, high speed segmentation, for example, in bioinformatics, in chemistry, astronomy, etc. So there has been this increased interest, but I would say that most research has been on detecting change points rather than making statistical significant statements about them. But there's a big need, there's a big demand for quantifying uncertainty in change point problems. Often frequently when I'm approached with a change point problem by applied scientists, one of the first questions they ask is this change point real? Is this change point significant? How can I be sure that I have a change point there? So there's a big demand out there for uncertainty quantification in change point problems. But the literature response so far has been modest, I'd say. So there has been some work, and I will review it very soon, but not nearly as much as work on detection. So just to give an example, here's a data set where, what is this data set? So this data set is the price impact on the market of making currency trades. So I'm a large trader, I'm a bank, for example, and I place, I trade currency, and I measure how the market responds to my trades, depending on whether my liquidity providers, or in other words, parties I trade with, how they, what they do to their risk, whether they match trades in-house, that they would then be internalizing liquidity providers, or whether they send off my risk to the third party, which means they'll be externalizing liquidity providers. So in this experiment, I trade first with internalizing liquidity providers, and then at some point I switch to externalizing liquidity providers, and I want to know whether this causes significant change in the way the market reacts. So I'm talking about the change in this data set in the average response. So I'm not talking about changes in the variance or in the second order structure in how the market wobbles after my trades, but I'm talking about the change in the average response. So I really want to find a change point, if any, in the mean or median or some sort of centrality measure of this data set. And you will appreciate that visually it's impossible to spot. So we're not talking about an exercise where I can have a pen and paper and mark my change point, and I'm sure there is one. So just to give you an idea, so I have this entire data set on the left and part of it on the right here, where it's pretty messy from the point of view of sort of statistical modeling. I have a lot of zeros, I have heavy tails, and etc. Okay, good. So I'll come back to this data set in a moment. Now, so what have people been doing in this area, in the space of quantifying uncertainty for change points? There was this pretty significant paper, which was a Royal Statistical Society discussion paper a few years ago, where the authors proposed this algorithm called SMUS. What is SMUS? SMUS is an algorithm for constructing confidence regions for signals, for piecewise constant signals containing change points. Now, how do I check whether my candidate fit is appropriate? I propose a candidate fit. I check the residuals from this fit. If the residuals look like residuals should, like white noise residuals, and I'll check it using a certain multi-scale norm, then I say, if they look like residuals at 95% significance, say, then I accept that my signal lies within 95% significance space. And that's all fine, but there's a problem in SMUS in that if my significance level alpha, so 5%, for example, is it 5% or 1%? If it's very small, then I have a very lenient test on my empirical residuals, which then in some way, I will spare you the details, leads to very counterintuitive coverage properties for SMUS. And I will illustrate that later on. So that's SMUS. There has been work on post-selection inference, which is, I believe, what Paul Fernherdt spoke to you about a few weeks ago. So what is post-selection inference? And you heard about it. It is detecting change points first, and then assigning p-values to those detected change points. You heard about it, so I'm not going to say too much more. What are potential issues with post-selection inference in change point problems? Well, there's it doesn't cover things like, for example, uncertainty in location estimation. Also, it talks about assigning significance for each change point separately, and also it relies on a Bayes method. So if your Bayes method for detecting change points is not very good, then you can't really. It may not be very informative for you to have significant statements of this type from the superimposed sort of post-selection inference method. Great. What else? Well, if you have a plain vanilla change point detection result, then often it is of the form that for all change points, my change point estimates lie within a certain distance of my true change points, with a probability going to 1. And these are, you may think, maybe let me try to just to try and so if I try to annotate, so okay, maybe I can't do that. Yes. So I still want to, okay, maybe let me not do that. Let me try to annotate using Zoom. Can I do this? Okay, let's try that. Now my question is, can you see this? Yes, okay. So for all change points, the probability of the distance between my change point yeah, and its estimate, probably that this is within a certain distance, this probability will go to 1. So maybe like this, or maybe we have for all eta under the probability. In fact, most often it is like this. So ignore that. So these kinds of statements, how useful are they for inference? They are typically not very useful for inference because when I look at this delta here will depend often on the properties of the signal, which I don't know much about. For example, minimum spacing between change points, or minimum jump sizes. So inferential statements of this kind are not very useful in practice, not to mention the fact that I have this convergence here, which again, I don't know if it's happening or not for my particular signal. But people study these things, and it's just that they are not very inferentially very useful. Okay, very good. So let me just get rid of that. Otherwise, you'll go on to the next slide, I believe. Sorry, it's a bit pedestrian, but I haven't mastered the required tricks yet. Good. So now, some people on top of this, they also provide confidence intervals for locations for change point location around previously detected change points. So it's this the second bullet point on this page. Now these are all very well, but these are confidence statements conditional on detected change points. So they are not unconditional. They are conditional on my detection process. So once I detect my change points, then I build my conditional confidence intervals. Okay. So also that it doesn't incorporate uncertainty of detection. This kind of statements. Okay, very good. There are other approaches. There are other people who make other kinds of confidence of significant statements. For example, there's a false discovery rate approach to change point detection, where I have a controlled overestimation of the number of change points. So I detect my change points, and I know that with a certain probability, I don't overdetect by too much. Now, with this kind of approach, that's a valid, of course, statistical procedure. But I would argue that it's not often very informative when it comes to determining if a particular change point is real, because I don't know if this particular change point I have comes in this overestimated bunch or whether it comes in the not overestimated bunch. So false discovery rate in change point problems, it's not useful for local information, for information about a particular change point. And there are Bayesian approaches. I don't know if Paul mentioned them to you. But I would say they are the most useful when clear priors are available about the number or the locations of change points. And I would say this is not always the case. Okay, very good. So what do we propose? We propose this slightly different way of looking at the change point inference. And this leads to this algorithm called Narrowest Significance Pursuit. What does it do? So the output from the algorithm is localized regions in data sequences, each of which must contain a change point at a certain global significance level. So for example, we'll be 90% sure that there must be at least a change point in each of my regions. And I'll demonstrate an example very soon. Change points, you may have been thinking of change points in the levels of a piecewise constant signals, and that's one example. But in general, Narrowest Significance Pursuit covers a fairly broad class of models where change points are understood as abrupt changes in the parameters of an underlying linear model. And in brief, how does it work, Narrowest Significance Pursuit? So it works by fitting my postulated linear model over many subregions of the data. And I will use a certain multi-resolution supremum norm loss for fitting this linear model. So I will not use OLS or anything like this. And I will identify the shortest interval in my data on which the linearity is violated significantly. And then I will simply continue this procedure to the left and to the right of my previously detected interval of significance. So that's the very short description of NSP, and I will demonstrate. Don't worry if you're not following this, I will demonstrate it graphically in the next slide. And to introduce it briefly, it works with a wide range of distributional assumptions on the errors, and it also allows autoregression in my data. So it's a pretty generic approach. And just to give you an illustrated example, it's not an example of how the method works, it's an example of the output. This is what it does to my data from the first example. So what are those red regions? The red regions are intervals in the data where NSP, Narrowest Significance Pursuit, has decided that there must be change points in the median of my data at 90% significance level. So in other words, we are 90% sure that there must be at least one change point in the median of my data in each of these intervals, in interval 1, 2, and 3. And this apparently, when I showed it to my collaborator from Deutsche Bank, he was very happy with this result. He said it agrees very well with the intuition from what it should be. So that's an example output from the Narrowest Significance Pursuit. Now, before I tell you in more detail how it works, let me tell you about the models it operates in. So there's a lot of text here. Don't read it all. Enough to say scenario 1 is where this function ft is piecewise constant. And I observe it with noise z. I will come to that later. So z can be Gaussian with known or unknown variance, IID. It can be light-tailed. It can be heavy-tailed. It can be heterogeneous as well. And then I do self-normalization. But I'll get to that later. So there's a very broad class of distributions for permitted distributions for z. Scenario 2 is also like this, but now f is piecewise polynomial. So it's piecewise. It can be piecewise constant, can be piecewise linear with continuity or not. It can be piecewise quadratic with continuity or not, etc. And I'll be assuming that the that the degree is known to the analyst, but I'll tell you also later what happens if I don't know the degree. That's scenario 2. Scenario 3 is where I have a linear regression model. So in scenarios 1 and 2, I also have a linear regression model. But my covariates, for example, in the piecewise constant model, my covariates will be, and I'm trying to annotate this again. My covariates will simply be all possible functions with a single break, single jump in each of them. So this is also a linear model. Yes, okay. In scenario 3, I'll do it with arbitrary covariates here. So they don't have to be piecewise constant functions with one jump anymore. They can be anything we want. And again, I will have breaks in those linear parameters beta here. Now scenario 4 is like scenario 3, but additionally I have autoregression here. So my YT, my response, can depend on lagged versions of itself here. So I have this autoregressive term here, which covers for me situations in which the data have autocorrelation. And I will show you an example at the end where this happens. So it's a very generic, and in addition to this, Z can be very general in terms of distribution. So it's a pretty generic framework. And how can I achieve generality like this? It's essentially because we don't do detection; we only do inference in some way. So it's if you like those kind of headlines, then this is not post-selection. Let me get it right. It's not post-selection inference. It's inference without selection, if you want, or it will also permit post-inference selection. So it will allow things to be the other way around. Okay, so it's not post-selection inference, it's the opposite. Good, so now don't read this, this is too much, way too much. Let me explain to you by annotation how narrowest significance pursuit would work. So let's consider scenario 1. This is my signal, very simple, 2 change points and noise on top of it. So that's my data. Okay, very good. This is it. What do? I draw randomly or deterministically many subintervals of my data. So maybe I draw this one and I draw this one. And of course, they are overlapping, possibly. And there are many of them. Okay, enough. In each interval, I check whether my linearity holds. And I do it by measuring this deviation from linearity. What is this function, deviation from linearity? I'll tell you later. I check my linearity. And then I choose the shortest interval on which my linearity is violated at a certain global level alpha. Okay. So for example, here, well, in this first interval, okay, linearity is not violated here because I have my locally constant model. Now here, linearity is not violated either. This long interval, maybe the linearity is violated because I have 2 change points in between the endpoints. But that's a pretty long interval. Can I do better? Yes, I can. Let me change colors. I found this interval here where linearity is violated, maybe, hopefully, because I have this jump here. And it's the shortest such interval. So it's the shortest interval on which my linearity is violated. Okay, good. I found this interval. And then I go to the left and to the right, and I do the same thing. I measure deviation from linearity to the left and to the right in the same way, in the exact same way. And I always use this global level alpha. Okay, that's roughly the main idea. There are some details which I didn't tell you about. Having found my short interval of deviation from linearity, I then look for the shortest significant subinterval. And this is important because sometimes my grid, my original grid over which I draw my intervals, is not fine enough. I need to refine it. So having found this interval, which is short but significant, I then do a sub-search within this interval for an even shorter interval. Yeah, it must exist because in the worst case, I choose the same interval again. Yeah. Good. So this is exactly what the pseudocode says, and it's all, of course, in the paper. How many intervals to draw? The more the more the better, subject to computational constraints. And my statements will be not depend. They'll be independent of the number of intervals drawn. So if I draw too few intervals, then simply speaking, I may detect fewer intervals of deviation from linearity. If I draw more intervals, then hopefully this will allow me to detect more regions of deviation from linearity, but I may have to wait longer. So that's the whole idea. So the more intervals I draw, the longer I wait for the result, but the more regions of significance I may be able to detect. Good, so that's the main idea. Okay, I should actually erase it because otherwise, again, it will go to the next slide, I believe. Good, it's all gone. So how do I now, we have this deviations from linearity in line 12. How do we now measure this deviation from linearity? And this is crucial. So I use this, so okay, so let's talk about the building blocks first. So I have this scaled partial sum statistic, and for any input vector y, I simply take, going from S, the start point, to E, the end point. This is simply the sum of the components of y from S to E, scaled by this scaling factor, by this normalizing scaling factor, so that the variance is, is equal if I have a homogeneous noise. Now, and I have this very well-known construct, which is the scan statistic, which is the maximum of the absolute value of this USE statistic over all intervals SE, which are in a certain set of intervals. So what sets of intervals will be of interest to me? Either the set of all intervals, that's IA here, or the set of all dyadic intervals. So the set of all intervals which have dyadic length, so length 2, 4, 8, etc. Good. Now, what do I do with this notation? How do I measure my deviation from linearity? So I've drawn my intervals, and on any arbitrary interval SM, EM, where Y is my response and X are my covariates, I fit my linear model locally in formula 4 on this interval. How do I fit it? I don't use OLS. I don't use maximum likelihood. I don't use anything like this. I minimize the loss I defined in the previous slide. So I minimize this norm, Y in double modulus with respect to a set of intervals, either IA, if I can afford it computationally, or ID preferably. Now, this is very, very important. How can I do this? How can I find a beta that minimizes this? I'll talk about it briefly later. Essentially, simple linear programming does the trick. Why do I need to do that? This is an important step. I need to do this to have exact inequalities, which will allow me to make exact and precise and non-asymptotic and finite sample significance statements later on. If I used OLS here, ordinary least squares or similar, then I would be able to obtain similar results, but they would be only asymptotic. They would only say that my significance level sort of converges as n goes to infinity to the right significance level, but I don't want to do that. I want to have exact finite sample, even for sample size 3. I want to have exact significance statements. And this is because I use this multi-resolution subnorm. So I use the same norm, the same multi-resolution subnorm to fit my linear model as I use to then check the residuals from the fit. Okay. So thanks to this, I have these statements, which are simple, but I'm only able to make simple statements like this because I use this norm to fit my linear model. So what are those statements? There's this very simple proposition which says that if I have an interval SE without a change point in it, so there's no change point that lies within this interval, then my deviation from linearity D on the left-hand side of the proposition, what is this deviation from linearity? Well, it's the multi-resolution subnorm of the residuals from my fits. Look at formula 5, it's defined there. In formula 5, how is my deviation from linearity defined? It's defined as this multi-resolution subnorm of my residuals from the fit. So beta 0 is from formula 4. I found beta 0 by minimizing with respect to the same norm. So in formula 5, we have the residuals from the fit measured with respect to the same norm as I used to fit the model in formula 4. And this is my deviation from linearity. So my deviation from the linearity, in brief, is the norm of the empirical residuals from the fit of my linear model, where the fit was done using the same loss. Now, back to the proposition, what does this imply? It implies that if I don't have a change point on my interval, then my deviation from linearity, trivially, practical proof is 1 line or 2, is not larger than the same multi-resolution subnorm of my true residuals, which I can't see, of course. And this is an important statement for me because it leads directly and easily to this theorem. What does this theorem say? This theorem says that the probability of having an interval where I don't have a true change point, let's say it again, the probability of having an interval where I don't have a true change point is bounded always and exactly and for any sample size by the probability of my true residual Z of their multi-resolution subnorm exceeding my threshold lambda alpha. So I'm shifting all my considerations to the domain of my true residuals, where I have a complete, there's a wealth of results in the literature which tell me how to handle this probability on the right-hand side here. Okay, so to construct intervals where I don't have a spurious interval with probability, any probability I want, all I need to worry about is this probability of the norm of Z, the norm of the residuals exceeding a certain threshold. Great, okay. Now, so just a few comments. So this bound in the proposition in the theorem holds for any scenario, for any covariates, and that's only because I use the same norm in fitting the linear model as I do to check the residuals. And this is new, I believe. I haven't seen this in the literature. So narrowest significance pursuit treats any linear problem in the same way, even if there's autoregression in the data. And this is in contrast, for example, so some people do, for example, Fang and David Zygmunt, they have two recent papers where they do, where they also have subintervals of the data and they do sort of detection within each interval. And they are able to make similar statements, really. They don't, but they are able to. But they operate differently for each scenario. And the reason they operate differently for each scenario, and they only covered scenarios, I think, 1 and 2 from my scenarios, is because they do detection at the same time. Whereas I operate completely the same way for any scenario. Give me any linear model and I'll do the same, I'll run the same algorithm and the results will be valid for any sample size. Because I don't detect, I only perform inference without detection, and I use the same norm, the same strange norm, to fit my linear model unusually as to check the residuals. Okay, so this is an important difference, I think. So as I said, there are those headlines of inference without selection, if you like, because I have those intervals where I don't tell you where the change points are within them. And this also enables post-inference selection. You can take your change point detector, if you like, and detect change points within these intervals, and they'll be automatically significant. You don't need to worry about significance because they are significant. They are within the significant regions. So this kind of turns the whole machinery of post-selection inference on its head, and essentially makes it redundant. It's pretty difficult stuff, as you will appreciate from Paul Fernhand's talk. You need to condition on the detection steps. The statements are, to me, not very easy to understand, not very easy to communicate. But I think this approach where I first do inference and then selection, which is counterintuitive maybe to a statistician, is in this case I think simpler. So also this aggressive focus on this greedy focus on narrowest intervals is also, I haven't seen it elsewhere. It's pretty new, I think, as being part of an algorithm. So it's an essential sort of part of the algorithm here. Good. What's that? Now, so the set of intervals returned by narrowest significance pursuit is not conditional on anything. It's an unconditional subset of the data where you have to have change points with a certain high probability, desired probability. You can request a probability of 60% and you will get that. So you can request any probability and you will get the corresponding intervals. This procedure doesn't claim to detect intervals corresponding to all the change points. For that to happen, you would need to assume things like minimum segment size, minimum jump size, which this completely doesn't do. So this operates without any such assumptions. And that's why it's not a consistent change point detector. The only thing it promises, let me go back a few slides just to make it clear. The only thing it promises is this theorem. It returns intervals to you and it says, we are 95%, for example, sure that in each of these intervals, there must be at least one change point. This is different from saying, I've detected intervals for you corresponding to all the change points. I hope you can appreciate the difference. Good. Now, so obviously this then, as in the second bullet point, this leads to a lower bound for the number of change points with the desired probability. So if I detect 3 intervals, then I'm at a given significance level, for example, I'm 90% sure that there must be at least 3 change points in the data, because I have those 3 intervals. That there may be change points elsewhere. For example, if there's a tiny, teeny change point somewhere, I may not even be able to detect it at all. But at least I know I have 3. Now, one important thing to say is that it's less straightforward than ordinary least squares to perform this fit here in Formula 4. But it can be done very easily. I mean, it's a simple linear programming task. and it's literally 10 lines of code using the very useful this LP solve package in R, for example. I'm sure there are others.
And sorry for the interruption. May I ask a question for the notation? So could you clarify again, what is the difference? What is the definition between of the two sets of intervals? One is I sub 1 superscript D, one is I superscript A.
Yes, thank you for the question. I superscript A is all subintervals of interval SE. So this notation here, if I had let me, okay, just a minute, let's make it very clear. I A, I'm getting quite good at that. Oh, I said it too soon. This is very bad, but you get the idea. Okay, so I superscript A subscript SE is the set of all subintervals of SE. So A for all. Okay. Now, D is for dyadic. I'm not going to write the whole dyadic because it'll be terrible, but I say dyad. The same as E is the set of all dyadic intervals. What are dyadic intervals? Dyadic intervals are intervals located anywhere, but of length that is a power of 2. That's all there is to it. Why do I use? So ideally, I would like to use this set, but computation may be slow. So apparently, there are algorithms which permit the computation of this norm, where I use my set I_O for I. Apparently, there are algorithms which can do it in n log n for me. What is n? N is the length of the interval. Oh. N log n. But I don't know where I can find them. I found this algorithm, an algorithm like this in a paper. It looks very complicated. I don't know how to implement. I don't know where it's implemented, whether it's implemented, etc. Whereas to find an algorithm which is n log n for the dyadic set of intervals is extremely simple. It's a first-year exercise. We can all do it. So for computational reasons, I use this set rather than that. So I use the dyadic set rather than the O set. But I will one day. I'll maybe try the I/O. I just haven't done it yet. Does this answer the question?
Yes, absolutely. Thank you very much.
Thank you. Good, let's go on. So I need to, I believe, erase this. Sorry for my inadequate Zoom skills. I'm getting a little bit better every day. Okay, good. Wonderful. So all I need to do is understand this probability in the theorem on the right-hand side, the probability of the multi-resolution norm of my true residuals. How does it behave? What does it do? Well, luckily, we have plenty of results in the literature, essentially talking about very fast convergence to Gumbel distribution. So it's essentially the scan statistic of think in the simplest case, IID Gaussian data. There are results. They are actually pretty recent, those results. They are not like from the 1950s or 60s or 70s. So, for example, I believe that this person, Zaka Kawluczko, wrote this paper in 2007, and then he discovered that David Zygmunt and one of his students did obtain the same result in 1995 in a slightly roundabout way. So it wasn't as explicit as Kawluczko phrased it in this theorem, but it was there, which actually stopped him from publishing this paper. This is an unpublished paper. The result is absolutely correct. I checked it numerically in many ways. It's absolutely fine, but I believe it's the only reason it's an unpublished paper because the same result appears in Zygmunt and Van Katterman in 1995, and well, tough luck. I mean, he didn't realize this, but I prefer this result because it's more explicit. Essentially, it gives us everything. It gives us the maximum exceedance, the maximum scan statistic. Note, there's no modulus here. There's no absolute value around USE. We do need an absolute value. To get an absolute value, it's a very simple two-liner, so it's very easy. So essentially, it says that the maximum scan the scan statistic is less than this AT plus BT gamma. This probability tends to the sort of the simple Gumbel distribution, extreme value distribution. This converges extremely fast. So I can use this result safely for many sample sizes. But if I don't want to use this result, then I can very quickly simulate also the distribution. So it's not a big deal. This is the only limiting result in the whole piece of work. So the only non-finite sample statement is this result, but I don't have to use it if I don't want to. If my sample size is 14, then I can just simulate 10,000 multi-resolution subnorms of sample size 14, and this will be very accurate as well. So that it's not because we're talking about a small but fixed quantile, for example 1% or 5%. We're not talking about sort of consistency where my quantile goes to 0. Yeah? So simulation is easy if I want to do it. If I don't want to do simulation, then these results are very accurate for very small samples as well. Good. That's that. So what else besides Gaussian? So of course, I'm sorry, this is for Gaussian. This is for Z IID Gaussian. I should have said this. What if I don't have IID Gaussian? Well, I have similar results for symmetric light tail distributions. I have results for Gaussians with an unknown variance, which I have to estimate. But can I get something else? Can I get more than that? I can get more than this, and I should. Oh, I don't know what this. Okay, that's all good. So. What if I have a situation where I don't know much about my noise? So imagine I have this sequence of noise variables Z1, Z2, etc., which are independent and symmetric, but they are not necessarily identically distributed. So I may have heterogeneity in the distribution. I may not know much about the distribution at all. So let's take a look. So VT, and I'm conscious of time, so I make it quick. VT squared is the partial sum of squares of my residuals. And I will assume that if I take the maximum squared residual, I don't know what this VT, there's no minus in front of the 2 here, I'm sorry. So if you look at, sorry, let me just get to annotation. I don't know what I did there. So this bit shouldn't be there. I'm just gonna rub it off. Okay, there's nothing there. Oh no, there is. I'm sorry, there is. Of course there is, because I'm dividing. Yeah. I'm silly. I'm sorry. Erase. Let's divide. Let's forget about this. Okay, that's all fine. I'm dividing by. So it's the wrong place. The minus basically. That's what it is. So yes, there's no minus. Okay. I'm sorry. You know what I'm trying to do. Please be patient. Bear with me. I'm trying to do that. Is this what it is? I hope so. I'm sure it is. Yes. Okay, good. So I'm dividing by the sum of squares. So if I take my maximum residual, my maximum innovation, and I square it, and I divide by the variance, by the partial sum of squares rather, then if this converges to 0, which it does in many situations, as you will appreciate, then I'm in my setting. Then that's good for me. They don't have to be identically distributed, but as long as this holds, then that's good for me. And this is apparently equivalent to the central limit theorem, okay, on the Zs. Now, what I found extremely elegant is that how to perform narrowest significance pursuit in this setting. And what I found really enlightening was the following. Okay, let me rub this off. So I'll go through this quickly because this is a bit technical, but it's very, very interesting stuff. Namely, what do? I take my, maybe let me get annotation so we know where we're looking. Oh. I take my partial sum of my residuals. So I make it a process. I'll let it run over t, and I divide it by the sum of squares square rooted at the end. So I divide by the sum of squares with a t, with a capital T, with a sample size t at the end. Now this process, it's not as simple as this. It's almost this process, this linear interpolation. I'll spare you the details. It's even more interesting than this. But let's say it's this process that converges to the Wiener process. You won't be surprised to hear this. This is, I would say, standard. But it converges in this special function space H0, which is not a Hilbert space. It's a certain Banach space. Okay, it's a Banach space with a norm which is given by this. That's the norm of this Banach space. What does it mean? Why do we care about what function space it converges in to the Wiener process? We care about this because if it converges in this particular function space, that this means that the norm of my process converges to the same norm in this function space of the Wiener process. But the norm of my process, and we can safely go to the next slide, the norm of my process is a suitably self-normalized statistic which will solve my problem, which will give me the required guarantees. So as a consequence of this beautiful convergence into the Wiener process, but in the special Banach space with this norm, I'm getting almost for free, practically for free, suitable guarantees on the behavior of this self-normalized statistic here. So now instead of my multi-resolution subnorm, which is a bit like having this without the denominator, now I need to self-normalize, and I have guarantees with respect to the corresponding Wiener process. So instead of simulating now IID Gaussians, I'll be simulating appropriate quantile of the similar norm, the same norm of the Wiener process. So I can also do it once and forget about it, and it's done, and I can use the quantiles. Okay, and this is only possible. So it looks like it's a very high level. It's a very high level way of looking at things. And we thank. I was very happy to. I was very excited about how functional analysis can help you do data analysis. It's not functional data analysis. How functional analysis, as in Banach spaces, can help you do your data analysis. Here is how we have this beautiful result in the appropriate Banach space. It directly translates to bounds on my self-normalized statistic, and it can allow me to do self-normalization for NSP. So now, how did I do how they solve the example I showed you at the beginning with the Deutsche Bank data? I should be saying I use this self-normalized approach. No, I use something even better. I didn't have time to tell you today about this. I use the robust version of NSP, which I'm not talking about today. It's not part of the paper. I'm working on it now. I could have used the self-normalized version, but what I have in the robust NSP is even better. Good, so we're nearly done. I just want to show you one or two examples. So this is a simulated example. I have this block signal. What is the block signal? The block signal is a signal which has change points essentially at the blue lines. So the true change points at the blue lines. The gray data are the real data, the observed data. And the red areas are the NSP significance intervals. Here I detect all my significance intervals have change points inside them as promised by the theorem. So the promise of the theorem is completely fulfilled. All the red areas have change points inside them. There are change points outside those intervals. These are the change points I didn't detect. I didn't promise to you to detect those change points. The theorem doesn't say I'm detecting all the change points. You can sort of see why I didn't detect those change points, because they are sort of in the side parts of the intervals outside the NSP intervals. So it's difficult to detect them. To make it easier to detect them, I can run NSP with overlap. I don't have to start, for example, suppose I detected this interval, here. I'm getting my annotation, as you can guess. Suppose I detected this interval here. I don't have to restart from the left end and from the right end. I can restart. I can combine it with a detector. I can then detect maybe this change point, hopefully, and I can restart from the change point location. And this will improve matters, or I can restart from the middle of this interval. This will improve matters in terms of covering more change points. But then, of course, I can't, if I do it with overlap, then I can't say then I have at least as many change points in my signal as I have intervals. Because some of the intervals may correspond to, some of the overlapping intervals can correspond to the same change point. Okay, but that's, okay, I've run out of time almost, so let me go a bit faster because there's a few, not many, one or two interesting things to be said. A coverage comparison, I wanted to get 90% coverage. So I wanted to have intervals which have 90%. In 90% of the situations, each of them contains a change point. And SMUs gave me that in 52% of the cases. So it's well miscalibrated SMUs. Okay, I think it's a miscalibrated procedure. I don't know what's got wrong there. It's miscalibrated. It's not, don't trust it. Whereas NSP delivered what it promised and more. So it's possibly too safe, NSP, slightly, because I have a few inequalities there. You saw a few inequalities. So it delivered 100% of realizations where I have change points in them, in the intervals. I asked for 90%, I got 100%. That's okay. That's over-promising is better here. Over-delivering is better than under-delivering here. What happens in so here's the piecewise linear example. What's wrong with the left-hand plot? So what's wrong with this plot? What is wrong in this plot is that I used the wrong model. I pretend that my covariates are the piecewise constant covariates. I pretend it's a piecewise constant signal. And then, of course, I don't have the coverage because I used the wrong model. In the middle plot, I use the right model. I have piecewise linear. I have linear covariates, the piecewise linear system. I'm getting my intervals around my change points as required. In the right-hand plot, I have a piecewise linear signal, but I'm using linear and quadratic covariates. So I use more covariates than necessary. But still, because my true covariates are inside this set of covariates, then I should be getting coverage. I should be getting interval or intervals which cover my change points. And I am getting them. I'm getting one which covers both change points. How to interpret the right-hand plot? In the right-hand plot, this interval depicts departure from quadraticity, from a quadratic. And it is a departure from a quadratic because it's a wave. So here I'm departing from a quadratic. Good, and one last slide, I believe. Yes, so it's a second and last data example where I have my data set is the average monthly sold property price, or sold real estate price in a particular part of London, in the London borough of Newham. What's so special about this part of London? It hosted the Olympic Games in 2012. Okay, and I'm looking at it on the log scale. So QT is the logarithm of this price. I want to understand if this autoregression, qt is a linear function of qt minus 1, is stable, or whether there are changes in these parameters. Okay, no problem. I run my NSP. It returns one interval of significance, which is pretty long, covers 5 years. So just assuming one possible change point in the middle, it may not be in the middle, but it probably is somewhere around the middle. I run 2 autoregressions, up to the change point and after the change point, and I see how the parameters change. So for example, the autoregression parameter A changes from unit root autoregression, so I have around 1 here in the first segment of the data, to well under unit root, to 0.92. What does it mean? How to interpret this? Well, if you look at this plot, in the bottom part of the plot, you get the data up to the change point. So bottom plot, up to the change point. In the top plot, these are the data after the change point. And you can visually see how NSP may have concluded that this is a change from a unit root behavior, from a sort of explosive behavior in the bottom plot, to more stationary behavior in the top plot. What's the story? Well, the story is the bottom plot, the part before the change point, it corresponded, for example, it included the part of the Olympic Games, so a lot of regeneration in that part of London, a lot of new construction. So property prices, of course, gone up. But in the top part, the part after the change point, we got a lot of sort of misfortune, everywhere, including London. For example, Brexit, departure from the European Union, and early stages of COVID-19. So times were less rosy in the second part of the data. So no wonder my property prices stopped exploding. Okay, so there's a nice story behind it, I think. Good, and I'm out of time, so I'm just gonna ask a few questions. What about online monitoring for change? Good question. What about gradual change? Well, another good question. Of course, if I have gradual change, then NSP, then if I detect an interval of change, then I must have at least part of that change within that interval. It cannot be no change with a certain global probability. Testing for time stationarity, I'll skip that, that's more technical. And post-inference selection as a headline in other settings, big question there, whether it makes sense or not. And the paper is where it is on arXiv. Thank you very much.
Thank you very much for your talk. I think it's very interesting and very, very insightful. Yeah, especially the result, the ideas you gave behind the results. I found them very illuminating. So now it's time for questions. Do we have questions from the audience? Okay, so I think I can open up by asking a question. So regarding this interesting term post-inference selection versus what people call post-selection inference, as you already said. So practically speaking, which one would be more relevant? That's a question I've been wondering myself after listening to your talk, because one is that you are talking about statistical inference before you select on the change points or you select a model, right? And the latter is that you first pin down those change points or a model before you do statistical inference. But I'm not very sure which one is more practically understandable or relevant. What do you think?
A great question. I think, so imagine a typical scenario for post-selection inference. I've already detected my change points, and I use this particular detection method, which is compliant with my post-selection inference machinery. It cannot be any detection procedure. It's not so modular post-selection inference. I can't have taken it from the sky and I think I have my change points here. What do you think? Give me the p-values. It has to be, they have to match the detection algorithm and the inference machinery. And then I can ask the question of, I detected this change point, how can I be sure that there's a change point there? I get a p-value, okay, fine, but I can't be sure, of course, that the change point is exactly there. I can't detect, change points is not something that you can detect with a consistent certainty within a point. There's always an error that you're making. So so because of this, perhaps it's more natural to speak of regions where you must have that change, because you can't speak of a point where you must have a change.
Yeah.
So if you speak of what this inference without selection gives you is it's a different approach which flags up for you red regions in the data where something's going on. Imagine, so if you, for example, were using this approach to online monitoring for change, you may well have you may flag for you a period of current anomaly.
Yeah.
Where for example, if it's a security application, something's possibly not quite right going on. You may want to increase your security because we are in this anomaly period where things are different from normal. Things are different from baseline, where the baseline is your linear model. Okay, so it's a slightly different viewpoint where we first flag up those regions in the data, where something out of the ordinary is happening with a certain global probability. What do we do with that? That's another matter. Maybe in online monitoring, we're not exactly interested in security applications. We may not want to detect change points there. We may say, okay, well, that's the anomalous region. I'll just increase my security generally. Whereas in the application I talked about, it may be of interest to detect exact change points there to see what's happening.
I see. So then in practice, how would you think of, so basically I can see that NSP itself can be used as an approach for detecting change points, right? Even though you cannot tell users exactly where the change points are, but you give them intervals. So they know, okay, if the intervals are really narrow, then the change point is roughly there. So then back to the change point detection problem, those algorithms, right, that can actually give you like just very accurate where the change points are, where the estimated change points are, but without inference. But I wonder whether in those algorithms, can they provide or allow some input of some level of confidence before they call those change points?
Yes. So, for example, in the work of David Zygmunt, he in his recent work, 2 papers from 2020, he computes. He takes, in one of the papers, he takes the piecewise constant model, and he computes similar results regarding the multi-resolution subnorm, but applied to the Q-sum, which is a change point detector. Okay. And then he is able to obtain similar intervals which come directly with detected change points inside them. But because he combines detection with inference, he has to decide on the particular linear model to operate in. So he's covered the case of piecewise constant signals with IID Gaussian noise. He has the results for the corresponding Q-sum detector, being a detector with IID Gaussian observations. If he wanted to do it in a different scenario, for example, or if anyone wanted to do it in a different scenario, then we would have to go through the machinery of how best to detect change points in that scenario. Not just how to check linearity. Checking linearity, what I've done, is easier. It can be done in the same way for any linear problem, and I've done it. But so the price for me to pay for this facility was to say that I'm not claiming, I'm not trying to detect change points there. I'm only trying to mark those intervals of non-linearity. Whereas if you want to do detection, then you have to go through, you have to go, at least for the detector, you have to go through the maximum likelihood or least squares detection. Then you have to obtain similar results for the detector, for example, for the Q-sum in the piecewise constant case, or for the triangular check function in a piecewise linear case. So for each scenario, it's a separate work.
Yeah.
Whereas I don't have to do any of this. For me, I'm only checking the residuals. I stand back from that. I'm not doing detection. I'm only checking the residuals. Checking the residuals is the same for any linear framework. That's why it's so general and so, in some sense, straightforward.
I see.
I can pair up NSP with a detector. I can, for example, detect an interval first, and then I can say, well, let me run a Q-sum inside that interval. I can do that. And it's nicely modular because I return an interval to you. I know that there's a significant change point there. So I know that my Q-sum is automatically significant. That I can do this, but it's not the same as getting this Q-sum as a detector and deciding if it's significant or not. Because I firstly decide that this is my significant region of the data, and then there must be a significant change point there. So detection comes after inference. That's why it's post-inference selection, post-inference detection, whatever you want to call it.
I see. Very interesting. I see. Yeah, so in other words, basically, if you want to detect change points, you need a stronger assumption. You need to specify what is the specific model, right? Instead of just detecting like the significant changes, like in what you did over here. You only look
Absolutely.
at the
Yes. You need to know what scenario you operate in, and you need to proceed accordingly.
Yeah. Okay, thank you very much for your answer. Do we have any other questions from the audience?
Hi, I have some questions, Jessica.
Yeah, please go ahead.
First, I want to thank Professor Fryzlewicz for the very stimulating talk. With regards to my question, my first question is, can this model handle the case of high dimensional settings where the number of covariates can grow even if the length of T also grows?
Yes, absolutely. So this can cover the number of covariates is absolutely arbitrary, but of course, if you have, for example, more covariates than the sample size, then your let me go back to the formula. So where are we? We should be here. If I have more covariates than the sample size, then my deviation from linearity will always be 0 because I will always be able to explain the data exactly. So I won't detect anything at all. Okay, so an interesting question would be to what extent this can be generalized by means of some sort of penalty or something, where this can still give meaningful results if the number of covariates goes to infinity with the sample size. It can go to infinity with the sample size, but if it approaches the sample size, I'll be getting likely no detection at all. Having said this, what are the interesting cases? So a piecewise polynomial model of degree D requires D+1 covariates. So a lot of interesting cases are already covered with a fixed number of covariates. But of course, I appreciate that there are linear models which are high dimensional, and it's very interesting to detect change points there. And then it'll be good to come up with something that mitigates this. Thank you for the question.
I see.
Good question.
Thank you. I have another question. With regards to the method, right? Can you say something about how robust the method is to miss a specification or data contamination? For example, I think some of the examples that you show, the errors are Gaussian or real data, right? What can you say when you assume a Gaussian model, but say the data is not Gaussian, but there are some outliers or some contamination?
Yes, that's another great question. Well, I wouldn't do that. I think it's safer not to make these assumptions, which is why I worked on this self-normalization. So the problem with self-normalization, as I explained to you today, is fascinating mathematically. It's this, I find this direct use of the functional convergence in the Banach space, direct application to your data problem. I find it super elegant, and I was stunned when I discovered it. But more importantly, perhaps, what I found was that the intervals obtained in this way are a little bit long. So if you have a very long interval, how informative is it? Well, it may not be very informative. So what I studied next was a super robust version, which only works with, which is what I'm writing on at the moment, which is looking at signs. So you draw an interval. So let's annotate this one here. You draw, wait. Okay. You draw an interval here. Okay, it's not going to be as simple as this, but just to give you an idea. Calculate the empirical median and look at the signs of your data above or below the above and below the median. So these will be pluses, these will be minuses. And then you only work with the signs. So you check, for example, if the signs align in a pattern, minus, minus, plus, there's no reason for me to put pluses. Okay, plus, 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 plus. Then this signifies a change point, yeah, because they are nicely aligned. So the minuses come before pluses. On the other hand, if you have a very mixed landscape, maybe you have plus and pluses and minuses, and it looks pretty random, then maybe there's no change point here. Okay, so there's no change point here, but maybe there's a change point here. And of course, there's loss of power here in terms of, so if my data were Gaussian, then of course I would lose something. Because I'm only working the signs, but I'm gaining so much in this way because I can treat arbitrarily heavy tail data. If you've worked on non-parametric change point detection, which you have, Oscar, then you won't be surprised to see all this, because in non-parametric change point detection, you're comparing distributions, and we only work with exceedances. So here I work with exceedances over the median. We may be working with exceedances over arbitrary quantiles, and then the situation is similar. So this points towards sort of non-parametric inference in this way. This can be done. The interesting bit there is, so there are at least two interesting things there. One interesting thing is that this approach gives much narrower intervals than the self-normalized approach that I introduced to you. And the other interesting thing is that the way, sorry, let me just go back to how I fit those models, how I compute the fits. And the other interesting bit here is, so I'm nearly done, as you can see. Okay, there we are. The other interesting bit is, if I do it this way, then I can no longer use linear programming to compute my fits. So I can no longer use my linear programming to compute my deviation from linearity if I only work with the signs. Again, you may be not surprised to hear this because of the nonlinearity of the sign transformation, etc. So I need to use other devices, and there's a whole sort of paper to be written about how to compute this deviation from linearity if I work with the signs, or if I do another sort of quantile-based approach. But it works very nicely. For example, on the data like this one, where I completely don't have to worry if I have Cauchy residuals or similar, and it just works with anything.
Thank you. And then one final question, Professor Fryzlewicz. The theory seems to require to have independent data, right? Even though it can be very general, not necessarily in the same distribution. Can you say something about the case where there is some correlation, time correlation?
Yes, absolutely. So if you remember, I mentioned scenario 4, where I can have autocorrelation. But the way I introduce autocorrelation is not by saying that Z here is autocorrelated. My Z here is still independent, but I introduce autocorrelation by putting in lagged covariates here in formula 3.
I see.
Sorry, lagged response. The lagged response in formula 3. So this is a way for me to introduce autocorrelation. So this is a way for me to model. Of course, I can rewrite this model to get a model a bit like in Formula 2, where I have some dependent structure in Z, but I need this dependent structure to be very particular, like in Formula 3, for me to be able to use the same machinery as I always use in NSP. So this runs exactly the same way as in any other scenario, but I have this, it absolutely permits autocorrelation. In fact, the example with the London house price data was pure autocorrelation. There was nothing else there but autocorrelation.
Thank you.
Thank you very much. Do we have further questions before we finish? Okay, so thank you very much, Dr. Fryzlewicz. I think I wonder if it's possible for you to share your slides to our audience after your talk. Yeah, that would be great. So if you could email me your slides, I can send it to our audience, and I think that will be very helpful for our PhD students to further study the details. Yeah.
Well, thank you so much. I'll certainly share the slides, and just to say again that it was a great pleasure and an honor to present here. So thank you very much for inviting me again.
Thank you so much. Yeah, okay, please take care. Yeah.
Thank you. Thank you.
Bye.
All the best. Bye-bye.
Thank you,
Take care.
Professor Fryzlewicz.
Bye-bye.
Thank you.
Bye.